now we're going to start looking further into these oxidation reduction reactions. So far we've gone through the electrochemistry. This is also electrochemistry, but I've labeled it specifically the galvanic cell. Essentially, this is a battery. We are going to make a battery. Those of you who use lemons and things before to do so, it's quite a fascinating thing to do, is it not? Now, let's just go back to basics. I want to just put in here that this is galvanic cells, right? It's electrochemistry because let's go back to, and I keep calling it Old Faithful. Old Faithful is the reaction that we can depend upon to tell us what's going to happen, and this is Cu plus 2, SO4 minus 2, copper sulfate, aqueous, meaning it's in ionic form, and this is a zinc solid. And remember what happened. And I do that a lot, the Zn solid changed. This is our reactant. This is our product. It changed to Zn plus 2 electrons. And what happened to the copper? It was a plus 2. It was aqueous. And the copper then changed to, the copper actually added 2 electrons. I'm going to get that away there. And this basically got 2 electrons and became copper solid. That is what happened to us, is it not? Now, we know that is spontaneous, but what is going on inside here? That's what's going on. There is a transfer of electrons. Okay? Let's just say that's a flow of electrons. What's a flow of electrons? It's a current. Current. So now we've said, hang on, this thing could be actually giving us electricity if we do this. Well, let's just do something interesting. What I'm going to do now, and you've got it in your textbooks, and please know it. Know how to label it as well. All right? It's not a difficult sketch. It's worth every point. From an examiner's point of view, to ask you to draw or label the parts of the cell and discuss it using 2 metals is a beautiful question. They ask you to do the oxidation, the reduction. And if you follow what I'm about to do, you can do it for any metals. It makes no difference. We're even going to see how the salt bridge actually works. Okay? So, what I'm saying is this. I'm just going to do a drawing here, and I'm going to draw it as nicely as I can. All right? Like so. And I'm going to say this over here is Zn solid. That. And in here, I've got zinc ions. I've got Zn plus 2 ions in here. Now I've got another pot next door. And you'll be right. I've got, let's say, copper sulfate in here. Okay? Plus 2. It doesn't matter. So I'm going to remove that so that we don't have to bother. It's basically rich in copper ions. And this one is rich in Zn plus 2 ions. In other words, you've put some salt in there and stirred it around. So there's lots of aqueous stuff. Okay. Now, the next thing is I'm going to put in over here. I'm going to put in a copper solid. These are called electrodes. I'm going to put a voltmeter or an ammeter over there like so. Or an ammeter, doesn't matter. Okay? Please bear in mind, all we're doing is measuring a potential or a flow of current. Now, if I connect this side and that side, then a current will flow. Why? Because what would happen is if we put, and this we're going to discuss later, just for the moment, I'm going to call that a salt bridge. Okay, I'm going to call it a salt bridge. That is to connect and retain electron neutrality. Don't worry about that. It's very simple. It sounds cool though, doesn't it? So we've got copper plus 2. Now, what did we say? We said that at this side here, this is going to be the oxidation. This is going to be the reduction. Okay? Oxidation is always at the anode. O-O. Anode, oxidation, ox, anode. All right? Reduction is then at the cathode. Okie dokes. And we just keep going up. Just let me just hold that there. And this is what is happening? Okay? I'm going to now look at what is happening at the zinc electrode. I'm going to come back to that sketch. Let's just take our zinc electrode. We said that's a zinc. Now, what happens is an ion pops off there, correct? And he becomes Zn plus 2. What does he leave behind? Okay, he leaves behind 2 electrons. So this becomes full of electrons. So this becomes negative. Okay, what happens on the opposite side? Okay, at the cathode is we've got the copper over here plus 2. It takes electrons away. Okay, this removes. This removes. This leaves electrons behind. This removes electrons, making this positive. So this one becomes positive. Okay. This is what is happening over here, and this is what is happening over there. The copper is removing electrons as it gets them, because what happens? At that surface, a copper ion comes along and it takes 2 electrons away, leaving it positive. Which means, ta-da, what's going to happen? It means that there's then going to be a current flowing. And as long as the salt bridge is there, it means there will be a current. If there's no salt bridge, okay, you won't get a current flowing. The voltage, okay, is then going to be measuring the EMF. There's a voltage which is that way, and there's a current which is flowing that way. Now, this is not, okay, we've got that there, the electrode. Okay, now let's have a look. What happens at the anode? Anode means oxidation. Okay, what happens? Well, it dissolves. We know that. Okay, it goes into solution. It dissolves, it goes into solution. What is the next thing that happens? The mass of the electrode decreases. You're saying, obviously, but you know, we're just making notes of what's going to happen. Okay? And simultaneously, every time that happens, the concentration of Zn plus 2 increases. Right? According to the equation, the equilibrium equation, Zn solid in equilibrium with Zn plus 2 electrons. Okay? So as long as that can happen, it will happen. Think about that. As long as it can happen, it's going to happen. Similarly, what now happens? What happens at the cathode? Okay, at the cathode, the copper plus 2 plates out. Okay, what do I mean by that? it forms copper metal. Therefore, the mass of the electrode gets heavier. Because each time the copper comes, it sticks on there. Okay, it keeps sticking on. Yes, this is how we're going to start looking at plating things with silver, copper, chrome. Okay, chrome plated, gold plated. This is how you do it. Not this way, but a slightly different way. But you're getting the picture here is that the copper is getting heavier. Also, the concentration of copper plus 2 ions, all right, the copper plus 2 ions decreases. All right, that's what is happening at the cathode. It's getting heavier, but inside this pot, we're using up the copper. We are using up the Cu plus 2 ions to become a solid. Okay, so we're using them up. We are using up the zinc electrode here, aren't we? We're using that zinc electrode up. So now that we've actually connected them with a salt bridge, and we're going to get into what a salt bridge does. Don't worry, let's just go through. Okay, this is an equilibrium reaction now, very important, all right? They are equilibrium reactions. Therefore, they depend on the concentration and temperature. Okay? They're depending on the concentration and the temperature. Okay? Now, because of this, we need to bring about a standard. Because if we don't, when I make a cell of my 2 pots, here they are. Here's my pots over there. When I make this cell, mine is different. I'm getting different current, different voltages. So we standardize. We standardize the temperature and the concentration. Very important. The temperature is at 25 degrees Celsius, which is 298 degrees Kelvin. How did I get that? Plus 273 degrees Kelvin, which is absolute zero. Remember that. Now, the voltmeter reads a potential difference from one half of the cell to the other. It's obvious because a current's going to flow. So, yes, that is what is going on over there. Now we've got a current flowing. We've made a battery because we can actually work with this. Righty-ho. What's the next bit? Well, the next bit is answering the question, what does a salt bridge do? Okay. Now, this is a question that's often asked, and it's not often explained very clearly. Firstly, number one, what is in it? Okay, you've got to know that you've got to have a seal at the one end and a seal at the other end, and you've got your salt in between. What is inside it? Generally speaking, the salts that we use are NaCl, KCl, KNO3. Okay, there are others, but those are the ones that we're going to be using mainly. All right. Now, let's just have a look at what is happening in our 2 pots. Okay, in pot 1, it's to maintain electrical neutrality. Let's just write that down. Number 1 is to maintain electrical neutrality. Right, number 2, all right, is to say, right, let's just see what that means. Let's look at pot number 1. Now, pot number 1 over here is we had the zinc. This is the zinc solid. Now, let's look at the equation. Zn solid is in equilibrium with Zn plus 2 electrons. So this one is actually dissolving, is it not? So as it dissolves, all right, bearing in mind that this has already got Zn plus 2 ions in it. It's got a concentration of zinc sulfate ions already inside there. Okay? Zinc sulfate ions, whatever. Now, they are already inside there. What does that mean? It means that this equilibrium here is going to occur very fast. Okay? So if there's no salt bridge, the equilibrium reaction in here, okay, there's no bridge joining, so this is dissolving, reaction runs to completion quickly and stops. All right? So what's going on? It means that essentially over here, I saturate, this pot gets saturated, and I'm using this in our terms. I'm not using it in terms of saturation coefficients or products or anything like that. It gets saturated with Zn plus 2 and stops. It stops dissolving. Why? Because no more can dissolve. No more can dissolve. So basically, forward equals reverse. Make sense? In other words, now I'm at the point where every zinc that dissolves, another one goes back onto the thing. So it doesn't lose mass anymore. The reaction essentially stops. All right? Let's have a look what happens on the other side. On the other side of the world, okay, we've got over here, we've got our copper solid over here. This is full of copper plus 2 ions. On this side, we use up the copper plus 2 because we've got copper plus 2 plus the 2 electrons becoming solid copper. Once again, I don't have to go through the whole thing. The forward and the reverse will happen quickly. I use up the available copper plus 2 ions until I can't use any more, because every time I use one, I release one. Okay? So now, okay, the salt bridge, okay, the next thing is then the salt bridge allows ions to move between the harm cell. Salt bridge allows ions to move between the half cells. What am I saying? Right. What did we say over here? We said that in this one, we are building up a concentration of Zn plus 2, right? And in this one over here, we are using up copper plus 2. So what is remaining over here? Let's say this was a sulfate. And let's say this was, I don't know, let's say this was a nitrate. Okay? You can see, let's rather leave it as a, I just want to keep it simple because of the molarity, the the moles. I'm going to leave this as a sulfate, plus 2, plus 2. Can you see, as I'm using up the copper, as the copper goes away, the SO4 minus 2, the SO4 minus 2 concentration is rising. So this side starts becoming negative. This side here, the Zn plus 2 concentration is increasing. More is being, therefore, this side starts to become positive in the pot. We need to maintain neutrality. This is not neutral. This is negative and this is positive. The Zn, bear with me, the Zn is dissolving into the solution. So more and more Zn pluses in this pot, right? And in this pot, my copper's going out, which means more and more sulfates. So this is becoming negative because I'm losing my plus ion. I'm losing my cation, okay? And in here, all right, I'm gaining, or rather I'm gaining cations in there, and I'm losing them on the other side, aren't I? So what is happening? I am becoming plus and I'm becoming minus on that side there. That's what's happening. So that's not neutral. Therefore, what do I have to do? I have to say, all right, let me draw in my salt bridge now. Okay, let's just put it in black, like so. Now let's say this salt bridge has got K plus and NO3 ions in it. Now, this side is getting positive. So what does it mean? It means that the NO3 comes in here. All right? And I form, right? Because that's coming in there, all right? It's being sucked in. It's keeping it neutral. This side, all right, what happens on that side? All right? Or if I use sodium chloride, the same thing. What happens is then my K plus is going this side. So my K plus is replacing my Cu plus. My NO3 is keeping the zinc happy. Okay? So, what if I had sodium chloride in here? Okay? The chlorine is going to go in there and the sodium is going to go that way. So, at the anode, it's becoming so full, the chlorine migrates to form zinc chloride or zinc nitrate, and it keeps it neutral. So it keeps this side neutral. Okay? So in other words, there is no build-up of a plus or a minus charge involved in these here. All right? That's what we're saying with that. So our salt bridge, okay, allows the ions to move. They move out of the salt bridge to maintain electrical neutrality. Why? Because the metal that's dissolving, doesn't matter what metal it is, the metal that's dissolving, okay, it could be a, I don't know, could be an aluminium, all right, over here. And this side could be, I don't know, a mercury cell, for example. So what we've got here is this one is dissolving, which means if I don't link it, I'm very quickly going to reach equilibrium. Over here, I'm also going to, because I'm going to be using up, and therefore I am going to have not electrical neutrality. This pot will be positive, that pot will be negative. It's not neutral. Remember, my pots must be neutral. I want to keep my current flowing through. The salt bridge allows that process to continue. Thanks for watching that one. We're going to carry on with this. There's quite a few more that we've got to get through, different cells and cell EMFs as well. Thank you for watching, and we'll be back and we'll carry on with the next one as soon as possible. Cheers. Bye.